All right, folks, today is Wednesday, December 16th. On Monday, we covered anomaly detection. Anomaly detection is a vast topic that has a lot of applications. For example, you use it for fraud detection. We use it in the medical sciences for discovery of diseases, tumors, and things like that. People are even using it to find anomalies in the heart condition. So you can use it for astrophysical data. You can use it. I mean, there's a wide range of places where anomaly detection comes in. It comes in for intrusion detection in networks when whether you're being hacked, banking systems, whether banks are being robbed. So the potential for using anomaly detection methods is vast. It's a huge field with wide applicability. As I mentioned, this field is just being an expert on this topic essentially gives it's a specialization in its own right. And usually there are lots of startups and big companies that are working only in this domain. It's a very fertile domain. And from what I understand, there are not enough people working in this domain. There's always a scarcity of talent for this space. So therefore, this topic is important. We covered the basics last time. It's a vast topic. I usually give, sometimes in the past, I've given twice, a dedicated workshop on anomaly detection. And those workshops were well attended, though the audience was slightly different. They came from specific companies or groups who wanted to pick up this topic, sort of like a private class and so forth. So today, we will do one part of anomaly detection. If you remember last time I mentioned that anomaly detection has two parts. They're classical methods, starting with very basic k-nearest neighbor or clustering and so forth, isolation forest, one class SVM, and there's lots of them. A lot of the algorithms you can repurpose to be anomaly detection methods. Now, anomaly detection, when you do, it could be supervised, semi-supervised, unsupervised, the whole gamut of it. You use it, and even reinforcement learning. And now, we didn't cover reinforcement learning in this workshop, but they are quite actually effective in this space. And so today we'll do labs. Much of the lab is using pre-existing libraries. The emphasis will be on getting familiar with anomaly detection. Once we become familiar with anomaly detection, we will have another lab in which we will create deep anomaly detectors from scratch. It's not that much of a stretch. We'll take our autoencoder code and we will now repurpose it, and we'll see how straightforward it is to repurpose it for anomaly detection. But that will keep after we have done a lab in which we have become familiar with anomaly detection techniques. So most of you are coming here after doing ML100 and ML200. So this year's batch, the one that started in March. So at this moment, you don't have familiarity with anomalies and outliers and so forth in a practical way. So we'll start with the basics. We'll see how it works and we'll work through some examples. A lot of the examples that I'll show you are actually taken straight from the documentation or adapted from the documentation provided by the libraries that we'll use. We'll focus on two libraries. One is scikit-learn and the other is PyOD. OD stands for outlier detection. I would strongly encourage you that after this week, as a homework, become familiar with it, apply it to a few data sets, create your own examples, play with it. And it is important that you know how to use some of these libraries. In the next lab, or in the subsequent lab, we will go, actually, this is a lab I need to do at some point. We'll do an extra session. We'll have to squeeze in a session coming to the end of the workshop here. So we will add extra session somewhere, extra lab somewhere, in which we'll build an anomaly detector using autoencoders and possibly GANs absolutely from scratch. Right? But that is a little bit more advanced than first becoming familiar with the anomaly detector. So that is the context for today. Right? Now, just to give you guys a sense of the roadmap of how we are moving forward, we are in the subsequent weeks. We are this is the 13th week. We have 5 weeks left. The last 2 weeks will go to projects. So I won't talk about projects at this moment. I think the feedback from last week was that people are just getting started and they are waiting for the holiday season to do much of the work on the project. However, I will start. Um, we'll cover the usual Saturday updates on projects. If anybody has updates, some of you hopefully have show and tells to do. Updates to show. So we will do that on Saturday. This Saturday we'll also have our quiz review. This Sunday we will have our paper uh, research paper review. There's a review paper on the optimizers used in deep learning. A group of people have sat down and studied no less than 40 optimizers and how well they fare across a fairly representative uh, real world situations. And the findings are quite interesting. We will cover that this Sunday. We will give 2 weeks or at least 1.5 week or 2 weeks, depending upon how much time it takes, to time series analysis. I also need to, but then that leaves us with two important topics. One is CNN, object detection. This is how, for example, very much used when you have automated self-driven cars and things like that. So that topic is important to cover in a deep learning workshop. We haven't done that, so we'll keep some time for that, and we'll keep some time for um, interpretability of AI models, which is again a significant topic. So we will be covering a lot of topics pretty fast and sort of brace up for it gradually in the coming weeks. I will be throwing in a few sessions, extra sessions here and there, just to make sure that we cover all the material that we have. Now, in the last 2 weeks, when we do the project, we'll give Monday, Wednesday, Saturday, and pretty much all 3 days to workshop a project coverage. And I'll be releasing solutions. I'll be hoping that you folks present your solutions. We will learn a lot from the projects. Now, the learning from the projects, I want it to be different from learning from the labs. In the labs, these are guided labs. I walk you through the solution. I will, of course, release a solution to the project and walk through it, which is a slightly bigger code base than what you have been doing so far. But at the same time, 1 week, when you folks, each of the teams will make presentation of their work, finished or unfinished, one way or the other, you'll be presenting your work and showing how far you made, and you'll be presenting it to your colleagues. So do be mentally ready for that. Now, furthermore, there's one more announcement. It is possible that I may not be here in the last 8, 10 days of December, 2 weeks. So Dr. Chanda, who is here with me as part of Support Vectors, and he does, of course, attend these workshops. He has been following. It is quite possible that if I'm not here, he will take over some of the sessions. It might be with either with object detection or much more likely with time series. So he'll be doing the time series sessions till I get back onto this. I have some fairly vital work that has come up in the workplace. I'll have to go and take care of that. Any questions, folks, before we start?
Who would that instructor be, please?
Oh, Chanda, you have listened to you have attended his talk. Most of you have. Remember the Sunday talk on word embeddings?
Yes.
Yeah,
He's good.
yes. So he'll be taking over two of the sessions. He's part of our little support vectors faculty list. So, and I think you'll like it. He's just to give you a bit of a background. He's an extremely bright person. He's those of you who come from India, you know about the IIT JEE. He's one of the top rank holders from that. Finished it, did his uh, thing from IIT Chennai, and after that came to US, did a marvelous PhD. Actually, I was together with him in the PhD program. We happened to be roommates, and of course, we have worked together for many years now. And of course, those of you, as you said, who have attended his talks know that he is very good. All right. So with that, one last bookkeeping thing: the quizzes, is the completion rate of quizzes is quite disappointing. Last week, Saturday, we couldn't cover the quiz review because almost there were just four or so completions. This week we have about 10, 11 completions. Some of you are in the process of have started but not finished it. Many of you have not started. Can I please request you to finish the quizzes? There is a lot of learning in the quizzes. So if you're not taking 10 minutes out for the quiz, it probably means you're not getting time to even review your books or read, do more reading on homeworks and so forth. So it means that, see, it can mean only one of two things. It means that we are moving much faster than you are able to keep pace with. Right. So those are the opposing forces. While we want to cover a lot of topic, what I am seeing is a lot of you are being left behind. The completions on the quizzes is a bellwether. It's a clearest indication of whether I'm moving too fast, right? And it has been the indication for the last few weeks that I may perhaps have been moving too fast. You guys are all busy and you're not able to catch up to it. See, at the end of this, if you don't practice, all that you have learned may gradually begin to fade out. You have to go back and review. Learning is cyclical. Please do take out time and learn and finish your quizzes. Right? Otherwise, it's a very anomalous situation. Some of you are insisting that we cover a lot of material, right? Which I am frankly willing to do. But when I look at how much amongst them there is a completion of quizzes or thoroughness in that, then the numbers are disappointing. And so I can imagine that even the labs you guys are behind, projects here. I know that on Saturday evaluations, when we do the reviews, projects, we are all far behind. So the reality is, guys, that we are moving pretty fast. Yeah. And in fact, you guys are giving me feedback. I should go even faster and cover a lot of topics. I'm totally willing to, but if you want to get things out of it, do take the winter break. There's holidays coming up, and do take time to finish off these things, finish off your projects, finish off your quizzes, all the quizzes, and do the labs and so forth. Uh, please do take care of that. So with that, I will get started now with the lab of anomaly detection. So as I said, this lab will do in two parts. One part will be just using the libraries that exist, and the second part would be building our own anomaly detectors. So let me know, guys, if you are seeing my screen.
You see it just fine.
Is it too small, too big?
Nice and visible.
Nice.
And so far the lab is running fine on my machine.
Okay, you already ran the lab. Thank you. So again, guys, all the lectures and labs are being continuously posted to the course webpage. For one thing, yeah, one more bookkeeping. This Sunday papers that we are doing, they are an integral part of this workshop. So the participation there is about two-thirds of you show up for the Sunday paper reading. Some of you are not able to make it. Understandable, we all have family responsibilities. But if you get a chance, do go and pick a few at least of the Sunday uh, papers. Read the papers and then watch our code review, the videos of the, not the code review, the paper readings. Paper readings is an important part of developing maturity in a subject. I mean, when I go back and look at my PhD years, the one activity that was most fruitful that we used to do was paper reading. See, the course, the subject matter is compared to the research level is fairly trivial, and it is things that have happened way back in the past, 10, 20, 30, 40, 100-year-old knowledge. It is in the paper that you catch up to the latest and greatest always. And taking a tough paper as forming a little group, reading through it, talking about it, and really being thorough at it, nothing gives you a more confidence and brings you up to the state of the art in the subject as paper readings, which is why I incorporated it as part of this workshop. So if you haven't attended the Sunday sessions, don't have to go and watch all the videos, but pick a few interesting ones and watch it. So last week, for example, we looked at how it was a more theoretical paper. It was about how a kernel, these deep neural networks can be reinterpreted or can be interpreted in terms of kernel machines or support vector machines. And that leads to interesting insights. This week, we are going to cover optimizers, and we are going to look at some researchers who have carefully paid attention to all the optimizers used in deep learning and seen how they compare against each other across a variety of real world tasks, as I mentioned. So do please do that. All the videos are there. All right, guys. So with that preface, let's get started. So we are talking about anomaly detection. Anomalies, well, are outliers, right? Or you can also call them novelty. If you have seen certain kinds of data, you have established a norm, a sense of normality, a representation of normality. Then you get a data point. All you need to decide is, does it conform to your representation of normality, or does it deviate from that? If it deviates, it's sort of novelty detection. People these days don't distinguish too much between the two words. They treat it as more or less synonymous. So people talk about supervised, semi-supervised, unsupervised, um, anomaly detection. And of course, the one topic that I, at this moment, I've avoided and won't be going into because we haven't done it is reinforcement learning. How does reinforcement learning contribute to anomaly detection? By the way, this is something I do cover in the, the anomalies workshop, but that's a separate topic. So today we will focus on using other people's libraries. And so there are classical methods of anomaly detection, there are deep learning methods of anomaly detection, and so forth. So we'll focus on only two libraries, scikit-learn and PyOD. Right? So remember that you can treat anomaly detection as a binary classification problem. Is a data point normal? Or is a data point does it conform to some definition of normality? Or is it an anomaly? So you could write a classifier, and one example is um, comes from the credit card fraud data. Now, credit card fraud data is something that I happened to cover last year in a boot camp that we took some participants through. And we did it in the context of seeing how well can we use a classifier to work for essentially an anomaly detection situation. There, the problem was fraud, credit card fraud, and how much we could use to detect credit card fraud with that. Now, when you think of normal data and anomaly, by definition, to the extent that anomaly violates your sense of normality, it's a rare event, right? So data comes terribly imbalanced. When data is so imbalanced, then the imbalance techniques such as undersampling, oversampling, they quite underperform. And then techniques like SMORT, which try to interpolate and generate more data between the outliers, they can get quite lost or misleading sometimes for reasons that we talked about in Monday's session. Namely, if your outliers span a bridge, a bridge over the normal data, then Smooth could quite likely create uh, sort of a corridor of outliers that runs through normal data, right, orthogonal to it. So those are some of the concerns, not necessarily orthogonal, but by somehow crossing it. So those are some of the concerns with Smooth and so forth. Today, Harini is going to kindly show her notebook to look at that sort of an approach and how far it takes us. And then, while that is a valid approach for anomaly detection, and it's a question of judgment. When does class imbalance reach the level that you need to treat it as a problem, more specifically as anomaly detection? So there are no clear-cut boundaries. Right? So, for example, let's say that 5% of the people or 10% of the people at any given winter season, as we are going through now, have cold and flu and so forth. So you take their temperatures or you look at some biometrics like their runny nose and whatnot. Now, the 10% of the people, let's say that they are positive cases of flu and cold. Are they anomalies, or it is just a classification problem in which data happens to be imbalanced at the rate of 9:1? Right? That line is blurred, and it's often a judgment call and seeing what works. Right? In the same way, when you look at X-ray images of patients, and you see some presence of some uh, areas of interest, right? Then, and from there, you want to infer if there are any anomalies in the lung X-ray. Is that a classification problem, or is that should we apply direct anomaly detection techniques? So the lines are blurred. It's a judgment call. One slides from one to the other. Of course, if the data is 50-50 divided, then it wouldn't be an anomaly detection problem. But a significant class imbalance is a call for anomaly detection techniques. They may be worthwhile. So that is something to keep in mind. Now, when you learn about anomaly detection and things like that, one thing that I would strongly suggest, at this moment, I've started with very simple data, toy data sets, because it's important to get a feel for these algorithms. But perhaps in the next session, or we may not get time in this particular workshop, there is a very good place. This is this, which is, F11. It is a site of lots of, where am I? ODD. This website, and there are many such websites. You can go to Kaggle dataset, AWS dataset, and so on and so forth. They all have a curated list of outlier detection datasets. The reason I gave this link in our lab is all these datasets that you see, many of them are very well known and well studied. In fact, I myself have worked on and practiced on many of these data sets. So it is certainly worth playing with these data sets. When you look at it, you can see that the outliers or the anomalies, if you look at the percentages, it goes from 5-6%, sometimes even 10%, or 15% of Wisconsin breast cancer data. I suppose that's what it is. MNIST with the 10% anomalies, and so forth. So there's a fairly big spectrum of how much and what proportion of data is anomalies, right? And what proportion is not. So you'll get a pretty good sort of a exercise by playing around with this. We have standard data, the tabular data. You have time series data, which you can play with. And then there's security related data. For example, this is a lot to do with, as I said, adversarial systems and so forth. And quite a few. right? There's video data for anomaly detection and so forth. So pretty vast field with a lot of data sets to play with. Huh? So, but today let's take baby steps. Now, that's the publicly available datasets. Today, I will start with two libraries. One of them is PyOD. So if you haven't yet, if you don't have it in your system, and I assume you don't have it, you want to run this, uncomment this line and run it, pip install PyOD. Right? Uh, Run that and it will install it on your machine. And after that, comment it out because you don't want to run it again and again. So we will take a few things from the PyOD just to illustrate. Now, this is a straightforward method. What we have done is you decide how much of outliers do you want. Let's say 10% anomalies, 0.1, 100 training example, 100 test example, or you can make it 1,000 or whatever it is. It doesn't matter. Play with these numbers. Number of features we took as 2 simply because well, the screen is two-dimensional. We want to be able to see that, but play with it with multiple dimensions and see how well it does. One of the things you'll realize is that in higher dimensions, detecting anomalies, it becomes harder. Outliers and all these things, it becomes much harder to do that because of the sparsity of the data. So that is that. Now you remember that we said that some of the simpler techniques are clustering and KNN. So we start with that. And here is what it is. If you go to this website here, the PyOD website, let me go to the PyOD website. Yes. You will see that it's a pretty worthwhile website to visit. You'll see a lot of implementations. So do you see all of these names? These people have implemented all of these algorithms. And so there is code and examples for all of them. I would strongly recommend that you, like for example, you take this lab and all you have to do is change one model to another. The rest of the code remains the same. Right? Import a different model and just feed the same data onto that. And one thing I find very useful is if you go to the API reference, you will get an idea. For example, how do you use the variational autoencoder? You can go and use it. This is it, VAE. The rest of the code that we have written will remain exactly the same. It is not going to change. You can use, and many, many things you can use, for example, from very simple things like, for example, KNN to obviously isolation forest to XGBoost to whatever, there's so many algorithms that you can, one class SVM that you can repurpose for the purpose to apply it to your problems. And changing it is as simple as changing the constructor. Instead of using the KNN constructor, you can use the VAE constructor, variational autoencoder constructor, right? And so forth. And that will serve your purpose. Just one simple line of change. So I haven't repeated those activities in the lab. I leave that as a homework because otherwise the whole notebook will begin to look repetitive. Right? So, but all you need to do is go. So for example, if you want to pick, let's say just basic PCA, how would you do PCA? You would just literally put this constructor there. You would say PCA instead of KNN. Likewise, if you were to go and do XGBoost, what would you do? Well, you would just put this one line there. Literally, that is it. If you look at the signatures, with minor changes, they're all specificities. But if you just use a default constructor with nothing in it, that's good enough for most of these situations. So that is something to remember, that you could use this library for that purpose. Now, in the beginning, once we generate this data set, it's generating X train, X test. So why are we doing X train, X test? You realize that quite often outlier detection is semi-supervised or unsupervised. Right? It is just to validate. If you know the answer, you can cross-check. Right? So I'll play with two data sets here. One are synthetic data sets generated by the libraries. The other that we will use is the Smiley data sets. I don't know, do you guys remember the Smiley data set?
Oh, yes.
Yes, that's right, for our clustering. So if you remember, in that data set, I deliberately embedded a lot of outliers, and we'll see how well these tools do for those outliers. So we take this KNN detection. So quite literally, the line 4 is the only line that would change in this library as you switch from one particular algorithm to another. So from that perspective, using this library makes it extremely convenient for you to use in practice for outlier, for anomaly detection. This is why I introduced you to it. So we generated some data here. Let's see how well it does. And I hope this looks like, and it follows a convention identical to scikit-learn, right? So X train, Y train, X test, Y test, literally the notations and everything is exactly like that of scikit-learn, which you are all familiar with. So this should look, even the signatures are the same, dot fit and so forth. Right? And then they give you some evaluation and visualization. When you visualize, you have two ground truths, or rather, the training dataset ground truth and the test dataset ground truth. The left column is the ground truth. Now let us see how well the predictions go. So a very basic KNN seems to have gotten the predictions like that, which is pretty good. Right? Here, it made some mistakes. One, two, in the test data set, this was obviously, I don't know if you would interpret it as a mistake because this seems like an inlier data point. So it works, KNN. Now, the thing is, this looks rather flattering. It seems that KNN would work. This is not usually true. If you try with larger data sets or with more noise, KNN is perhaps not the best one to do, especially for higher dimensional data. The problem with KNN is, are all neighborhood-based methods is they work very well in low dimensional spaces. We are looking at two-dimensional spaces. In two-dimensional spaces, the neighborhood-based methods are very good. The trouble with them, of course, is that as you go to higher dimensional data, the feature space is extremely sparse, and your neighbors are very far off. So the word neighbor, its sort of meaning becomes questionable. Are they really neighbors at that moment? Right? So in lower dimensions, of course, you can do, and for any of these, one fact to bring about, uh, you can always build ensembles of your model. Whatever you do, you have hyperparameters, throw in that, run through that. And this example is literally, again, it is not something that I created. The library people have this example in their directory. It's a very good example. And I thought about it if I could add something more to it. And I realized it is such a simple, straightforward thing, it's hard to add. So the first part of it is very simple. You generate the data, so on and so forth. But the only important thing is here, the only change that has happened is now you're looking at many values of K, right? You take a whole set of values of K and go through that. It's a K list, 10 neighbors up to 200 neighbors. And then you just iterate through this. Now, we have done that in different aspects of our lab. When we did our KNN lab, you remember, we sort of did a hyperparameter search over the values of K. So that is exactly what's happening, nothing new. The rest of the code remains more or less the same. Right. Now they introduce a few notions which they have explained. Like when you look at it, take the average of all the base detectors. Like, are you saying, is it an outlier or not? Take the average of all the detectors. If the majority comes out that it is an outlier, mark it as an outlier, or use that to create a anomaly score. Maximization simply means that of all of them, take the biggest score, right? Then so on and so forth. And so you can play around with these. Um, Then you could also generate data in clusters. This is nothing new. Now, one of the basic algorithms is this LOF, local outlier factor. What it basically says is that a simple way to see if something is an outlier is by doing a local examination of it. if a point is sitting in a if one region of the feature space is less dense or has less neighbors than your neighbors, then you have a problem. So for example, your distance to the nearest neighbor is 2 miles, but those neighbors that you reached, your nearest neighbor has other neighbors within 100 feet of them, right? Now clearly you are an outlier and they are not. So that is a basic idea that local outlier factor uh, looks for. Right? It's a very simple argument that sparse regions contain outliers and and dense regions contain inliers. Right? That is it. It's a very so again, these are methods that work well in low dimensional spaces. The moment you go into higher dimensional spaces, neighborhood-based methods, it is a neighborhood-based method. These arguments begin to get into trouble.
Asif,
Yes,
the data set that we're using right now for this lab, what's the dimensionality of the data?
2 dimensions. Remember, number
X
of
and Y, that's it. X is only one.
X is a 2 dimensional.
Okay.
X1, X2. Huh?
Oh, yeah.
Y is
X1.
the label. Y is the label. It's typical, this scikit-learn convention that Y you reserve for output or the label. X, capital X is the vectors for
Yeah.
X. So,
Got it. Yeah.
yeah. So clearly, if you see here, this data is a little bit more on the clustered line. This is the training data set, and this is the prediction. The predictions are fairly good, except in the training, there's actually flaws. For example, do you see this triangle sitting in the middle of inliners? There is
Yes.
no reason to consider them outliers. So one of the nice things is that the test data set is pretty smart. I mean, the predictions from this is good. It doesn't consider those as outliers. Right. So see, when you look at data in 2 dimension, it can be pretty misleading. You may come to the conclusion that, oh my goodness, the simple methods work so well. But try it on MNIST or something like that. And then you realize that when you're looking at data at 786 dimensions and so forth, it begins to sort of degrade pretty much. Right? You need more powerful methods, but that doesn't come through because at this moment all the data sets I've taken in 2 dimensions. So what is the purpose of doing this lab? The purpose is, guys, to become familiar with these libraries. You will use it in your real life quite a bit if you are in this space. These are easy to use. As you can imagine, this code looks like your typical scikit-learn code that you guys have taken with me before. It hardly even merits explanation. For example, do you think this sentence or this line of code merits explanation, guys?
Straightforward.
Very straightforward, right? It's just using the
Decontamination,
library.
is that like adding noise?
That is right. And all it does is, by the fact that it follows the scikit-learn convention, means the learning curve is close to zero. The only meaningful line here is LOF. Do you notice that they use LOF? Right? And now pay attention to these 3 lines because it's using LOF here. But whereas here we used, where am I? We used KNN. Do you notice that we just changed one line between the two algorithms? I mean, the two code bases are practically identical. The only change is this. That's all, right? There they use KNN, here we use LOF, and that is about it. Which is why, I mean, I was just thinking, is there any value add if I were to rewrite the code in some different way? At the end of it, I realized that it is the same thing you end up rewriting. So I've left it as such. Um, so this is the clustering part of it. Now, what I would suggest is today in class, uh, play with this, change the parameters, change the number of data points, change the number of clusters and so forth, and see how well it works. So your homework literally is to go to these examples and change the values, change the number of data points and play with that. And I would rather, because now that I know you guys are very busy and you're hardly even taking the quizzes, I want to give the last hour to your just doing it here before we end the day, because otherwise you won't get time from what I can make out. Now, what does it mean if you use this library? By the way, they give you a comparison on their website of how it is if they used. They have done a comparison of all these creators of Pi. Actually, Creator, I think it's a one-man effort of this, has created a comparison between various anomaly detectors. And at the end of this comparison code, there's this beautiful picture. I want you folks to go and look at it and see how well different anomaly detectors have worked. Right? They have taken a few methods and applied it to this. So you can see that each of these algorithms is approaching the same data in a slightly different way. Do you see how these pictures differ? Right? So they all are taking a slightly different notion of what is anomaly and what is not, and so forth. What is inliner? So orange areas are inliner, and see how different algorithms are. They sort of resonate with each other to quite an extent. The first one doesn't, right? But rest of them more or less resonate, but they seem to approach, if you look at the surface, if you look at the way the anomaly score propagates across the feature space, from the color map, you can see that they are all thinking in different ways about the data. Like same data, different approaches that these algorithms take. And it again speaks to the variety and richness of algorithms in this space and the fact that nothing is perfect. It goes back to no free lunch theorem. Namely, for any is the data that decides which algorithm ultimately resonates best with it. The assumptions of which algorithm or approach of which algorithm resonates best with it. So that is something. And so do please go and pay attention to this particular diagram. Think over it for some time. Right? You don't have to spend time looking at this code. It is very simple. It's the same code with now a for loop. They're going through many algorithms. That's all. Like here, they're going through many algorithms. Nothing special. I mean, you can read through this code. You'll realize that it's exactly the same thing, wrapped up in a loop of many algorithms. That's all. So then, and I think to their credit, this Pi Odi, the person who created it, the developer, to his credit, he has made it very simple that at least the algorithms you can quickly go and use. How would you use a variational autoencoder? Now you would think that we will sit and build one, which we will do in part 2 of the lab. We will build these deep neural architectures from scratch, right, from the base up, and then we'll train it to do anomaly detection. But today, just become familiar with it. Now, again, the code. So he uses an autoencoder. The only change, of course, is using this library, you don't even need to know deep learning at all. All you're doing is, for all you care, you may not even know what an autoencoder is. You just change it to the name of this algorithm, autoencoder. Rest of the code, again, exactly the same. It's just repetition of what came above. And so, yeah, but once you run it, of course, you realize what happens. The model, you see, these are the things in your model, 300 layers. Right? You go from 300, 300, 300, 300. It's a pretty significant. Then to 64. Dense, 300, 300, followed by 64, followed by 32. You see the narrowing down, the bottleneck, and from 32 back to 64, back to 300, right? And so there it is. And then you run the number of epochs, is running it for 30 epochs. You can see that the loss begins to fall. Now, what is the point of autoencoders? Just to remind you, you train the autoencoder only with normal data. Realize. So in the language of anomaly, the outliers versus novelty, you will consider it more of a novelty detector. It creates a sense of normality. And then you feed it data and you see how well it does in capturing the outliers, right? Because the outlier data anomaly data will cause it to have a huge loss in the output. The loss because it doesn't know, it hasn't seen that, anything like that. So it will try to match it to the closest thing it knows. And so you will end up with significant loss. So this is a recap of the theory we did on Monday, right? And so Again, as you see the reason I'm not going into this code is this code is absolutely no different from the previous paragraph code, which is no different from the other previous paragraph code. It's the same code, but the only difference is this. And the niceness of this algorithm, this library, is that you get the benefits sort of out of the box. The next thing we'll do is apply it to the Smiley data set and see where we are. So just to recall, this was the Smiley, and this was the data set that I created, if you remember. And if you remember, this gave you guys no end of trouble when you tried to use a k-means or hierarchical clustering. Do you remember that, guys? That k-means and hierarchical were a disaster. Do you remember why
Yes.
it was a
Okay.
disaster?
Because it wasn't as neat of clusters, the different clusters.
Yeah, for multiple reasons. First, this data has outliers. Secondly, the clusters are not convex. They are not globular. When clusters are not convex or non-globular, for example, the eyebrows and the lips, they are essentially non-globular. Then k-means and the easy clustering methods, k-means and hierarchical, they get into trouble. Right? So you have to use, and one thing, if you recall, we applied density-based clustering, and that was quite effective. Let us go and apply that again. This is just bringing back the code from the previous slide. But for those of you who join deep learning directly, I think it would be of benefit. Density-based clustering looks for dense regions, and then everything else that doesn't fall in the dense regions is outliers. We covered or recapped the theory on Monday. So this is the data that I had produced. By the way, this is, so you may wonder what mathematical function I used to create the data. I didn't. I literally sat down and drew this picture and then extracted the data out. So, so now let's see what we do. When I run this DB scan, it marks the clusters. I've deliberately marks the clusters with colors and the outliers as gray areas. So you can see that it is pretty effective in finding the outliers. Would you say that, guys?
Yes, and very nice visualization.
Yes, thank you. So that is that. Then comes another novelty detection method. Right? And by the way, novelty detection, I'm using it here to be aligned with the scikit language. But generally in the field these days, as I said, people don't distinguish too much between outlier and novelty. They instead, quite often you'll see the word, especially in the deep learning literature, people saying supervised, semi-supervised, unsupervised reinforcement learning. So this would be like semi-supervised. Why semi-supervised? You have to carefully feed it only the normal data so that it internally creates a representation of what is normal. Right? So there we go. This is the data. So here is the part, and I will take one class is here. We'll first go generate the data. So this is the data we generate. So this is a little bit of a trick. What you have to do is go and pick 2 points and then around it, sort of go generate a lot of data. That's all. Uh, Nothing fancy here, just some playing to create data. So I've just, now what is the training data? Do you notice that in the training data, there are no outliers, isn't it, guys?
Yes.
No outliers. So this is the data, and I wanted to emphasize the point that this is the data that will feed into our one class SVM. So when we do that, the code is exactly two liners, even with a scikit-learn, and this is scikit-learn, one class SVM, and you go fit to it. That's why the nice thing with PyOD is it is aligned with scikit-learn convention. After that, you just go and check how much it worked and what the error rate was and so forth. And then you visualize the results. This visualization of the result, by the way, this code is a typical code that you find in scikit-learn. It's very nice in the library. It helps you divide the feature space by the anomaly score. So what is it saying? It is creating this, it has created this red line. I don't know if you can see that. Do you see this red line here?
Yeah, we can.
The oval? Yes.
So it is saying that these are my regions of normality, right? It has, this is my definition of normality. Anything that is out of it is to various degrees an anomaly, right? A deep blue is soft anomaly now, and the lighter blues are big, more and more. The lighter it is, the more anomaly, the higher the anomaly score, right? The more anomalous it is, and the more it deviates from the definition of normality. So when you look at this one class SVM, would you say that it seems to be doing a fairly good job?
Yep.
It seems to be doing a pretty good job here. So that is that. Um, then, likewise, we have another algorithm we talked about in the class the last time, which is the isolation forest. What was the point of the isolation forest? Unlike random forest, where you go about splitting at points of maximal information gain, in isolation forest, you relax it. You split at random points, right? You in rectangular regions of random points. And when you do that, then what happens is, and the same thing, again, the 2 lines of code, everything else remains the same, just these 2 lines of code. By the way, this generator code here is exactly the same as the generator code we saw a little while ago, right? Nothing different. And this is the visualization code. Because it was all identical code, except for 2 lines of change, I've put it all together in one place. When you do that, see what the isolation forest has done. It has marked these red points here. I don't know if you can make out the colors. These outliers are red, and the inliers are all with white and black, right? All these points have a black border, but the inside of inliners is white, which is hard to tell because it all just becomes big black. And here it is red. Maybe the red ones I should make it stand out. Red and S is equal to, let me do this. Let me make it 50. Let us go and generate this. Yeah. Now do you see that the red ones are standing out? Let's make it even bigger, 100. Let the good. So now you see the outliers standing out. I mean, the anomaly is standing out, isn't it?
Very clear.
Yeah. So that's that. This is isolation forest. Now you can train an isolation forest in a purely unsupervised manner or as a semi-supervised, in other words, as a novelty detector. So in the unsupervised, you'll feed it all data. If you feed it all data, it seems to do a pretty good job, right, in picking it up. On the other hand, if you want to feed it this, okay, so sorry, I take that back. Isolation forest is only works with unsupervised, like you have to give it all data. You can't treat it as a novelty detector. I take that back. Now with isolation forest, there is one problem though. This is a problem with random forest, etc. Also in isolation forest, do you notice that it creates like a Manhattan kind of streets? All you seem to get the sense of these streets when you look at the outlier, these boundaries, what it has created lanes which have the same outlier factor, isn't it? The problem with these kinds of perpendicular distinctions is, do you see this red point where my mouse is pointing to, guys?
Yes.
See, it has marked it as a very soft outlier, isn't it? Do you see the light blue sort of a corridor that is all around it? And this point also, it has marked it as soft outliers, which is problematic. But because if you really think about it, this should be a hard outlier, isn't it? There shouldn't be a soft outlier. It's pretty far from both of these. And so that's a limitation because of the, what it does is that if data is along a diagonal, then at the other diagonals, I mean, the other street intersections, the points that are there, they tend to not be recognized as strong outliers, right? The outlier score is, or anomaly score wouldn't be that big. So this problem, obviously, the easiest way to fix that is don't go perpendicular to the axes. Just make random directions. So it goes to the point that I was mentioning. One of the lessons people learned with decision trees and with random forests and this whole tree-based algorithms is, and it came rather late in the day, that many, and in fact many, almost all cases where we were bifurcating along the perpendicular axis, along the axis, if you changed your algorithm to go in random directions instead, right? Random slopes and intercepts, basically random directions when you split, then generally the performance of those algorithms, they increase, right? And that's a very good observation, right? Because it removes these artifacts that it is only making decisions along perpendicular regions. I mean, rectangular, so grid-like regions. It doesn't happen anymore. So, for example, for extended isolation forest, we can go to an example. The original paper is here. I've given a link to that. The summary of the paper is very readable. So it goes on to say that we extend the model of anomaly detection for forest, for isolation forest. This extension we called extended isolation forest. We motivate the problem. So basically somewhere it says that all they're doing is you take random directions. So here we go. Yeah, so the street, perpendicular kind of a street. This is not the best example that they take. Yeah, this is it. So what happens is, if you look at this example, which is the example that we are taking, what happens is if these and these are the inliners, they're this ghosting effect. This place where my mouse is in the off diagonal places, they begin to look like soft outliers because they are sort of it. This isolation forest lays things in a grid. If you want to avoid that, what you do is you go in random directions. And when you were to go in random directions, you have, and of course, they take a deliberately crooked way like this and try to find outliers and so forth. And then they point out that if you were to use standard isolation forest, you would be in a pretty bad situation because a lot of regions will come out as soft outliers. So now, instead of going, like you notice that this is it, perpendicular directions, you go instead, so they describe the whole problem. At the end of it, this is the gist of what they're saying. If you just go in random directions, right? Then what happens is, this is how your regions divide. And the effect of this would be, which is shown. There's a lot of arguments on why this works and so on and so forth. So let's go and look at the results. So you look at this, compared to the standard, by the time you get to the extended, you notice that it is doing a much better job of doing it. But more particularly, when you look at this data set, the sine wave thing, the first one, the isolation forest, is a bit bad. Extended forest does a pretty good job of creating or following the data and creating those soft score, anomaly scores in a more coherent manner. So it's a huge improvement, specifically for these two diagonal data set. You notice that in the standard IF, you have this ghosts of region that don't get well categorized. But when you go to extended forest, it seems to do a very good job. Right? So compare the leftmost with the rightmost. Do you see the improvement, guys? Is it easy to notice that?
Yes.
Yes.
Fewer lanes, less
That is
ghosting.
exactly. That's all it is. That's it is. And so I've given a link to a more readable article towards data science, on the medium.com. You may want to follow through, like if you don't want to read the whole paper, a much more readable version is here, which literally takes the images from the paper and explains it. And this is it. And you can read this paper. But at the end of it, the idea is exactly that. There's nothing new to it. Then, for sake of completeness, I put then, we did the local outlier factor using the PyOD. Now, this is using the local outlier factor using the scikit-learn. No difference. So even the sort of a constructors look similar, very similar. So it's your choice which one you use. When you do this, outliers, and you This code should be straightforward now with the scikit-learn background to all of you, which is why I'm not going over it line by line, uh, given the simplicity of the code. Yeah. We are all familiar with scikit-learn, NumPy, and so forth. So when you apply that, see what it has done. It has put circles around. The radius of the circle is the strength or the score, outlier score. A smaller circle means very soft outliers. Bigger circle means big outliers. So if you look at this diagram, you would agree that it seems to have done a fairly good job, right? And so, and again, I must warn you that when you are in low dimensional spaces, the neighborhood-based methods, simple as they really shine, right? If you remember when we did ML200, one of the things I told you is that if your data space is low dimensional and you have a notion of distance, use neighborhood-based methods. They will beat all the sophisticated methods, right? Or at least match them very well. It's cheaper, it's very effective. The same thing is not true, of course, the moment you go to higher dimensions. The problem with neighborhood, otherwise all of machine learning would just be neighborhood-based methods. So in higher dimensions, we start getting into trouble. So this is it. Now, you can treat this local outlier factor in two ways: as go find the outliers, give it all data with normal data inliers as well as outliers. Or the other thing is that and this is just a specific feature of scikit library, you can give it with explicitly say that, when I'm training it, I'm telling you that you're going to get only inliner data. So what happens when you train the same thing with pure inlier data only? Well, you train it, the rest of the code is exactly the same, and you can again use it to find so-called points of novelty, which would be your anomalies. So when you do that, it creates a region of normalcy. Do you see that it is creating a red-lined region of normalcy around the data points, the normal data points?
Yes.
Right? And so after that, radiating out from that, it will start creating the regions of different uh, anomaly scores around that. And as you can see, it seems to do a pretty good job. The new abnormal data, it's yellow in color. I don't know if it shows so well through this gold. Let me do this. Size is equal to not S, but 100. Or why 100? 200. Let's make it stand out really big. Okay. Now do you see the anomaly standing out? Right? Except that the yellow point, we are trying to do anomaly, but because we're creating random point, it accidentally got created inside the region of normality. So this system will, of course, consider it not abnormal, but normal data. Right? And that is it. So one nice comparison. So today, guys, I want you guys to play with this in most of the lab. Actually, do the lab. Right? So instead of me just walking through more code examples, let me see. This is a nice comparison for scikit-learn of their algorithms. I showed you PyOD's comparison of their algorithms. Now this is a comparison between 3-4 of the simpler ones, 4 of the simpler. I didn't cover the robust covariance. It basically says, what if we put a bell curve around normality data, right? I've rarely seen people use it. I don't use it, so I didn't cover it. So you see how these algorithms are faring with respect to each other for different anomalies, right? Different sort of regions of anomalies and so forth. Right? Each column. So these are 1, 2, 3, 4, 5 different kinds of data. And you see how each of the 4 algorithms work on these 4 kinds of data. Right? So guys, today we have had one of the shortest guided labs. The reason for that is I want you folks to use the rest of the time to the last 1 hour to do the lab on your own. Go and play with this and change these values, change the data set that you have. And for example, in PyOD, try different algorithms. I've just given example with a KNN and with the LOC, LOF, and with autoencoders. But there is a long list of models that they have. Go play with different models and change the data set and just do this lab here so that in case you get busy, it's holiday season, you're busy with kids, then you would have at least some practice. This lab is all uploaded to the website. So please download it or put it in your notebooks directory, in the where the rest of the notebooks are, put it in there. That is it. So in other words, it is here in my case. Do you notice that if I go up, this is all the notebooks. So where you have all the other notebooks like autoencoders, etc., unzip this anomalies directory, right in that directory, and you'll be done. Right? When you go in there, you'll find that you have. And here is the smiley data set that it uses. It's all there. And the rest of it is straightforward. So you'll get to it. So that is our anomaly detection, or at least this is using anomaly detectors, not building one from scratch. We will do the building one from scratch later. Let's consider this a slightly phase part 2, or a more advanced part. But we need to do that at some point. We'll take out time and do that. But at this moment, it's very important that even if you don't get time to delve deep into creating anomaly detectors of your own, in practical life, you won't get that. But what this lab is something that is far more useful for practical life, knowing the libraries and using them. Right? Having said that, there is still value in understanding how to create anomaly detectors from scratch, and we'll do a lab on that. Especially, with the deep anomaly detector. The only ones that I'll do is with autoencoder. And we'll build it up from scratch. In fact, that was the reason I was leading up to, I paid so much attention to anomaly detectors. I will deliberately use the variational autoencoder. I did not walk you through the code of the variational autoencoder, and I will be doing that. So that will also be an instance in which some time is devoted to seeing a practical implementation of variational autoencoder. Remember, the theory was a bit complex. The internal representation was not just, you didn't care for it. You specifically insisted that it should be a Gaussian, the hidden representation. And you sampled from the Gaussian. So that theory, how does it get realized in terms of real code for variational autoencoder? We'll look into it. So guys, at this moment, the state of the art is, in my experience, most of the time my own good thing is I always go and create a variational autoencoder for my purposes. Whenever I have to use it, I'll start with that. And then I may go on to more esoteric. Like, for example, there has been further developments. There's a Wasserstein autoencoders, new family based on optimal transport. We never got time to go that deep. And of course, it also gets more mathematical heavy. And that's where the cutting edge is at this moment. But it's a stretch. First we have to learn to walk before we run kind of a situation. Maybe in one of these Sunday research paper reading, I may do the Wasserstein autoencoders. But this is it. So it is 8:20 now. Let's take a break. And after that, please do the lab if you can. And the guided part is over. Any questions before we take a break?
No, this lab works very smoothly.
Yep. Actually, Asif, I wanted to say that it was really smooth. Everything went through no hitches and was able to follow through every line. Thank you.
Excellent. Thank you.
Exactly. I completely concur with Premjit and Kate.
Totally delighted. The whole experience was very smooth.
Nice.
Yeah.
The lab went really smooth today. Yes.
Yeah, so I would like to, before you guys break out, I would like Harini to present her work. She has done very good notebook on the fraud detection using what we would consider a supervised learning approach to detecting the anomalies of the fraud. So Harini, would you like to share your screen and take us all through that?
Sure, sir.
Asif, I have a question. Probably, I will pose it in after Harini's presentation.
Sure. Yeah, do that. So while Harni, while you please share your screen whenever you're ready. So guys, anomaly detection. Once you, the steps of learning is, or the maturity progression is, first you learn to use other people's library. It takes care of 90% of the situation in the workplace. Then you learn to create your own. Like for example, I have created my own anomaly detectors, which are variants of GAN and variational autoencoder sandwiched together. Then you go further. You take somebody's research paper and sit down and implement it, right? And we will do that also. I will take one research paper, maybe Wasserstein's, and we'll just implement it from scratch and see, um, take you through that and use it for that.
Yes.
Generally, what will happen is when you have a large project, there is a budget to it. Like, how expensive is it to miss some cases? So anyway, I'll give you one second before I let you speak. The point is that the way the game is played is that which is more expensive, letting those anomalies not be detected, or the developer time that goes into creating and researching a better and better anomaly detector. So suppose you are a bank, or you are one of those highly sensitive data places. The cost of missed anomalies is extremely high, prohibitive cost. You may suddenly be out of 10, 20 million in the blink of an eye, with one anomaly point may represent that you missed. So there you put in a tremendous amount of effort, continuously researching, looking into the data and creating custom models that only works well for that data. And ultimately it comes down to that. You end up making a super optimized model that has no application anywhere else except for that data. And it's a progression. It takes a lot of effort. Most people's situation is such that 90% of the situation, use the library, are done. Another, like I would say 9% of the situation, create your own code, implement your own anomaly detectors from scratch, especially using deep learning techniques, and you are done. And the final 1% hard problems are the ones in which you just keep on researching and you keep on failing. All you can do is fail less, right? And the business will be fine with that. I mean, they'll keep hoping that you keep improving. No amount of improvement is good enough in those situations. Go ahead. Somebody was saying something. Somebody was asking a question, was it?
Yeah, Asif, I was asking the question.
Yeah, go ahead, Shiv.
So you said you had to build something yourself. Can you give the example? What prompted you to build your own?
That is NDA. I can't talk about it.
Okay.
Mhm.
All right.
But I can give you, hang on, let me give you a flavor of it. See, what happens is when you have a data where it becomes important to catch anomalies and they're hard to catch, all of these libraries, they sort of work. They take you close to the solution, but then you realize that it is not good enough. You have to sit, research, find research papers, see what they have, then start from there, implement them from scratch. A lot of these papers, they don't reveal their code. So you have to sit through, deconstruct it, build it, then improve upon that specifically for your data set. So that's what it comes down to, basically.
Got it.
Go ahead, Harini. Please show us your nice lab.
I hope you can see the screen.
Yes.
Not
So,
yet. Oh, there it is.
okay. Yeah. So this is the credit card fraud detection data set taken from Kaggle. And it has around 31 columns. So time is one of them. And V1 up till V28 is PCA transform data.
Yeah. So Heidi, one second. By the way, guys, this is real data taken from European transactions. I believe around 2014 or 2016. And the reason those features have been so opaque is because data anonymity is very important in this space. So they have done that to enforce it. But this is not toy data. This is real data. Heidi, please go ahead.
Yeah, and classes are target variable, whether it's fraud or non-fraud. Okay, and so we have 284,807 rows of data, 31 columns. There's no missing values. This data set is pretty clean. And this is the basic thing. And this is our class distribution for fraud and non-fraud cases. The fraud cases are very like less than 1%. So there's a thin green line here, but yeah, we only have 492 cases out of all these fraud cases. So it's a very imbalanced data set. Okay, and here is just the, the analysis of how much the mean of normal data and fraud data. Here I have just plotted according to the amount, whether fraud or non-fraud, just to see if, I could get some distinguish something here. But fraud, the amount was very high on fraud cases, but not very low, nothing I could find here. That's the only thing I could come up with when I plotted the amount.
Yeah, so one thing, if you could go up, see guys, this is the problem. This I happen to know is the problem. The people who do fraud, right? We think that they'll suddenly do a bank heist, charge $10,000 or $1,000 onto your credit card. No, they're pretty smart. They buy your credit card info probably in the black market, and they make tiny transactions so that unless you are careful, even you won't notice it on your statement. It's a fact. I mean, I personally forget. For example, rarely, I always feel guilty that I should sometimes look at my credit card statements. I don't get time, but by not looking, you make yourself vulnerable to fraud.
Asif, one silly question on this. So
Yeah.
whenever like these fraudsters, if they buy from your credit card, you usually get a notification on your call, right? Like this particular purchase has been done. So
Yes, yes. You
like
get an email. You get an email typically, isn't it?
yeah, even you get a messages stating that like if this is because they see the location, which is like usually not in their regular locations where you usually buy from.
Yeah.
So they are. So is it not like a common thing over there? That's why it's easy.
See, this is 2014. All of these practices have been gradually evolving. We are learning from experience.
Okay.
Now it is the norm that, we do two-factor authentication sometimes.
Mm-hmm.
We do these credit card companies are very aggressive. If you yourself do a normal transaction, you try to fill gas. In my case, if I'm driving down the California corridor to Southern California, and sometimes I like to take the scenic route, and I'm going through the Joshua National Park and all of that. So is that the right national park? Yes, I think so. So anyway, you go through all of these territories, and you go to a gas station to fill your car up. You're in trouble because the first thing the credit card company machines notice is that you have never been in that area.
Yeah.
So they mark you as fraud. And so now I've gotten into the habit of always calling them and telling them what is my travel path.
Okay.
But yes, now much better. Even if a fraud happens, if you're checking your emails or your messages, you'll know that something has happened.
If I can chime in with a little bit of context to what Prachi asked us a question right now. I'm aware of one of the credit card companies which is working with, a company that I worked with earlier, right?
Yeah.
The models that they use for credit card fraud detection, it runs into the thousands. They actually, when the transaction is in flight, they use an early signature to figure out which model to pick to do the secondary check. So they're fine-tuned it to the extent that depending on certain transaction parameters, they pick an appropriate model to use as a secondary level of check. So it's gone that sophisticated right now in terms of how the credit card companies are deploying it.
Nice, interesting.
So it's not one model. They actually have several models.
Yes, you have an ensemble. Nice. Thanks for that input, Harini. So yeah, this is a good plot. Nice.
And now I tried to see the time,
Mhm.
what effect it has on fraud and non-fraud. If you see here,
So what is the X and the Y axis? They are not labeled. Could you tell me what are they?
this is the amount
Yes.
and this is the time.
Oh, time when those amounts are charged.
Yes.
Do you see
Scroll
any?
down just a little, it'll show the time on the x-axis, right?
Yeah. Sorry, Kate, I didn't get you.
Oh, no, I knew if you scroll down that the lower normal graph would show the amount in time in seconds, like you were saying.
Yeah, okay. So, but here, if you can see, there is not much of a difference between fraud and normal. Here, I think they're overlapping, both of them. So I couldn't distinguish them based on time too.
Yes.
And
No, so it is about the dollar amount.
Yeah.
It's like this normal dollar amount and what time of the day those transaction happens.
Right.
and this is our heat map for correlation. Okay, because it's already PCA data,
Yeah.
there's nothing much we could get even from correlations.
That's right.
And in this data, the time and amount was not scaled, so I scaled it
Mhm.
and just put it onto the data set. And here I've just tried to do the scaled amount and scaled the thing. I just tried to see if there was an overlap between the classes for time count. So that didn't happen. Here I did a pair graph to seeing each variable on against fraud, like if there's a clear separation between any variables. Yeah, so except a few of them, everything is overlapping.
Right.
There is no clear separation,
Yeah.
except a very few of them that I couldn't distinguish much there.
Yeah.
Then did the
If I may just say, this is very typical, guys. Whenever you're looking at anomalies and fraud and things like that, the signatures are very subtle. It's not that easy. So a single variable analysis, like you do on a feature wise, like she has done, you must do it so that you get some sense of it. But generally, the signal is very subtle and hidden in most of the situations. You go ahead.
And so I'm dividing it into the target and features here, and then doing the train and test split.
Yeah.
Directly on the data set, and just checked if there was any missing values on the thing. Here applied decision trees directly onto my data. I haven't handled my imbalanced data set just to see what how the model would be. Precision was pretty good. I would rather say overfitting, not sure though, but
Yeah.
this model seemed to be okay, but I think it is overfit data.
Yeah.
And that is because it was classifying mostly the fraud cases
Yeah.
because of the
See, what
imbalanced
happens is,
nature.
in a situation like this, the most sensitive measure, the one that I look for, is the recall of the positive case. So one is your positive case, fraud case. If you look at the recall, it is 76%, which means that 24% of the fraud you miss.
Yeah.
Decision tree is missing. That would be the way to interpret it.
Yes. And here also, yeah, here as Sir said, I'm more interested in precision and recall for this data set more than accuracy.
Yes.
If we want to catch all our frauds, it's okay if we say non-fraud as fraud, but we want the frauds to be right. So
Yes.
yeah, this is our confusion matrix and heat map, and this is the support. And here you go, the ROC curve.
Very nice.
Here you can see there's a few data points that are out. And
This is the ROC curve for the class, the fraud class. So that seems to be close to about 90%.
90%, yeah.
90, yeah. ROC curve of 90, yeah. Go ahead.
And this is our precision.
Yeah, precision recall.
70. Yeah, that's just give me a second. I'll just charge it. Okay. So after this, I have handled. Okay, I'll just take out this.
Your font has become a bit too big.
Oh, okay.
Just zoom out a little bit.
Control minus a couple times.
Yeah, better now?
Yeah, much better.
Okay. Okay.
Oh, too small. Yeah, good.
Yeah, okay, this is good. So now I have handled the data set, like handled the imbalanced nature of the data set.
Yes.
So by doing resampling techniques, okay, so first one I tried was undersampling. So here what happens, the minority class is the majority class records are reduced to match our minority class. So only a few of non-fraud cases are taken matching the fraud number. Both became 492, 492. So this resulted in a lot of information loss. And the next one is oversampling. I did the direct oversampling method. Here, it copies our undersampled data, like the minority class, and try to match our majority class. Here is what Asif sir was talking about, SMORT technique. Here, it finds the k nearest neighbors and the cluster points, and that points are imputed into the data set to balance the data. It creates synthetic data points.
Yeah. So this interpolates between the outliers and fills it in.
Yeah. Okay. So now I applied logistic regression on all the 3 data sets to see, what gives us better model. So here using undersampling, our recall was 93.
Yes.
And precision here for fraud cases is really low. Accuracy was 97, but yeah.
Right.
So the precision was, bad here. And here you can see.
So it's basically marking a lot of cases as fraud, good cases as fraud cases.
And even here it is, 8 cases it got wrong. So
yeah, it made 2,500 mistakes approximately.
Yes. So it's not good. ROC curve looks okay.
Yes.
But here you go. It says 98% precision, but I don't know.
Yeah, no, precision is okay, but the recall,
recall is high.
Stuck to that other end,
yeah. And here I used the oversampling. Here also, you can see it is very similar to undersampling. Yeah. Here the mistakes are reduced though.
Slightly, yeah.
Slightly, yeah. And ROC curve is okay. Again, it's average precision and is 99. Here then I used the SMORT technique. Here you can see the recall is improved, 98, 94. But again, the precision is low, but 98%. This seems to be better in all the 3 data sets. So I'm using SMORT data set to do the rest of the analysis. Here you can see it's significantly low, the mistakes compared to the other 2 data sets. So here you go. The ROC curve is also better. This is also better. So I just did the threshold plot for the logistic regression using SMORT here.
Yeah.
So you can explain this if you want to.
Yeah, no, this is all right. So the basic message actually in these situations, right, some of these curves, they begin to lose some of the interpretability or validity actually. The best way to look at it is directly staring at the confusion matrix. So if you go and look at the confusion matrix, you notice that you're still doing a lot of false positive and false negative. Type 1, type 2 errors are significant, right? So for example, you are like in this particular example, you miss, I believe in this particular case, miss about 7 cases out of approximately 120 cases. but you have a huge false positive rate. 1,700 cases are marked as false positive. So the whole question is that tolerable? What is the impact of that, and so forth? So that has to be, that is the main problem with these methods. So continue on this, Harini. Now apply the anomaly detectors that we have and see how well it does.
The best model I could get was decision trees
Yes.
on Smart.
Yeah.
And even random forest performed really well.
Yeah. So show us the confusion matrix. Yeah, this is very good.
Random forest.
Yes.
Yeah. And even I got the features that were important.
Yes.
So here, as our graph showed, V14, V10, and these are the 5 important features.
Nice.
That we could, use to do our SVMs or further analysis.
How did SVM do for this?
Pretty bad, sir.
Pretty bad, eh? Yeah.
Very bad.
The reason is you're looking at PCA data.
Yeah.
So there's not much chance to go to a good hyperspace, to a good mapping space, because it's already gone there and come back with PCA. So good.
Okay, so that's it. And I'm trying to do the autoencoder bit, but I'm stuck somewhere here so that we can go about
it. Right. So hang on, you're implementing it from the scratch?
Scratch, yeah.
Okay, very good. Very, very good.
This is what I did this, but...
Yes, very good.
Yeah.
And you are, okay, nice, good.
So 30 input features. So I'm just using 30, 15, and then 15, 30.
Yes.
To matching the input and output size and
I would say that your internal dimensions, you don't need to keep it 15. Keeping it to 8 would be already good enough, I think.
Okay.
Try that out, see where it
is. Okay, I'll try that.
Yeah. And remember that when you train it, you only train it on normal data, with the label 0. You don't train it on all of it.
Okay.
That's an important thing to remember. Go down.
Actually, here, this is okay. The model is coming up, but
the learning rate is a bit aggressive.
Yeah, I was just trying, but here it says it's not defined, but I have defined it.
You may not have run that section.
Run that cell or something. So,
sometimes you have to restart and run the whole kernel. Sometimes you get weird messages.
But very good notebook, Harini. Very good progress and very good notebook.
I'll just work on that and get back. Sir.
Yes, do that. Excellent. All right, guys, any questions? Any other thoughts? Otherwise, the guided part of the lab is over. Please use the rest of the time to take your break and do these things on your own. The reason I am sort of keen is that, you committed the time till 10 o'clock today to this workshop. So hopefully with your family. So why not use this time to finish off the lab? Go play with it, change the parameters and see what you can do with it.
Asif, Sudhir here. The question what I have is, when we went through this 100 dataset workshop, we, spent time across this scikit-learn, LOF, one class SVM, local outlier factor, all those stuff. But PYOD is that something specific to deep neural networks, or even we can use the same for the traditional?
No. They contain a whole mix of classical and deep learning methods. They're positioning. See, here's the thing. I don't think this project after that has evolved very much. We can see the last commits on it, right? But somebody made a very good effort to put all of the anomaly detectors in one place.
Okay.
It was really an admirable effort. I don't know how much it is followed, but when I look around the landscape for open source libraries for this field, there are not that many available, right? And this is I would say, pretty good library out there. So do please play with this. It contains everything from basic KNN and LOF, etc. One class SVM, all of those are there. When you look at scikit-learn, it just contains 3-4 of them, right? One class is SVM isolation and this.
Yes.
But this one is a much richer. It has a list of approximately 30 algorithms. 30, it should be enough for you to get your work done.
Okay. Okay. Makes sense.
Right? Includes deep learning as well as normal thing.
But
What's
Nassif,
the base version for PYOD? So
Come again?
what is what is the foundation on which PYOD is built on?
Oh, they have written, you can look at the code. Let's go and look at that code. If you look at this PyOD, hang on, they have given all this thing is here. See, this is a beautiful thing, right? The PyOD, sorry. Yeah, this is the, by the way, this is nice. Let's go appreciate this particular creator. He's a CMU. Carnegie Mellon is a top tier place. In fact, the top tier place at this moment in computer science. And he has created this library and pretty respectable, a very good library. I must have been, he has put in certainly a lot of effort. If you look at the source code, let's go look at that source code and you'll
you're
see.
not sharing the screen.
Oh my goodness, I am not indeed. Yes, so let me go back and let's pay tribute to this person who has put in so much effort to doing this. This is it, Yu Zhao, and he has created it. He's from Carnegie Mellon, PhD. By now, let's hope he has graduated with his PhD. Very well liked. He has a lot of followers, right? And CMU is, of course, the top tier place at this moment in computer science. And if you look at this particular PyOD, you notice that it has received 4K likes, and people are watching it. If you look at when was the last time things were updated, hang on, we can find that out by going to the notebook.
10th of April 2019.
That is right. So you can pretty much imagine that he got his PhD around that time, and he has moved on and become busier. Oh no, he has improvements. See, last month is the PyOD last improved categorical generation last month. So he's still maintaining it, it seems. Right. Here is the insights on active pull merge. Not that many people, but this is it. So if you look at the code, I guess the question that you asked is, the code is very straightforward. Like, for example, let's go to the autoencoder, because I just taught you guys the autoencoders, isn't it? So if you go and look at the autoencoder code, he's used TensorFlow, but even then you'll be able to figure it out. Hidden neurons, activation. So here, build model. Do you notice that it's a very straightforward build, like layer by layer, no different from PyTorch. And there is no magic. There's nothing extraordinary about the code. It is the very straightforward code that you would write. We have written that in PyTorch, he has written. But to his great credit, what he has done is he has taken the time to write it for all sorts of algorithms, even very basic ones, like, for example, KNN. Putting it all together in one place in a uniform API so that you don't have to fiddle around with different things makes sense and very well documented. If you notice, he has taken quite some pains to document it properly. And nearest neighbor is nearest neighbor, right? This is it. You just save some elements and then you just do a comparison with them. Then whatever else that you want to look at, a local outlier factor or some other, start with some of the simpler ones so that they make sense to you. But the nice thing is that he has put in efforts to make it aligned with scikit-learn. Right? You notice that he has put in effort so that things are aligned with that. Right? I would suggest that you will learn a lot simply by reading through his code. So here it is, one class SVM. Once again, if you look at the detection, do you notice that no one file is too big? He has a lot of comments, but when you, and then you can read through that. But when you read through this, nothing very odd. And in fact, he has used the one class SVM from scikit-learn, right? So what is his value? If you're just using scikit-learn, then what's the value of his library? His library value is he has given you a common interface so that with one line change the name of the model, but the same code, you can do anomaly detector across detection using so many different models. Do you see the value of that? That is it. Very neatly done and well done. So that is it. In terms of deep learning, he has not gone too far. Autoencoder is about the only one. XGBoost is here. I don't think he has used many, 2-3 deep learning libraries I think he has used. I mean, a model theories he has used. We can go to the documentation and see which ones he has done. Installation somewhere here. Yeah, implementation. So if you go, so do you see a long list of implementation? And all of this, you have to just change one line of code to be able to use any one of them. So that is the point. He has put it all together. Yeah, so all of his implementations are, these two are variational, I mean, these are autoencoders, and this is GANs, generative adversarial networks. That is it, guys.
Asif,
Yeah.
for training on the project, how much text do you generally need to have?
Sorry, I don't know. To train a project, what is the?
Yeah, for the project, the training part,
yeah.
How much text do we generally need to have?
You see, this particular, the eloquent transformers, you can get away mostly with pre-trained models and occasionally fine-tuning. So fine-tuning, you don't need too much data.
Okay. Yeah, okay. Thank you.
Yes. All right, guys, so that was the topic of anomaly detection. Should time permit, at some point, I would like to do an out of session sometime, an extra session whenever I get time, to just show you how to build autoencoders on your own. In the meanwhile, you can just go and read this code. See, none of this is hard. It's all very straightforward. And if you become familiar with the technology gradually, then it all becomes easy. You know all the theory now. We have done generative adversarial networks. We have done just about everything. So read this. So let's go and see how the SoCal is done. Yeah. So this is it. Well, he has done it with TensorFlow, so you'll have a little bit tougher time becoming familiar with it. But if you know the theory, you won't see. You see, what do you have in a GAN? Generator and discriminator, right? And you keep switching between training the two back and forth. That's it. The entire implementation is like including all the code, and more than 50-60% of the lines are code. So the total implementation is barely 100 lines or less, 60-70 lines. Very easy to understand, right? So create generator, the only thing that matters is your decision function, create generator. That's all. From gal base. So he has put it in the okay, gal base. Here is where he creates the generator. We can go and look at what generator he creates. Create generator. How does he do? Oh, yeah. So this is it. This looks pretty similar to PyTorch also, isn't it? Except that the word wouldn't be dense, it would be the word linear. Linear layers. So no mystery to this. One good thing with deep learning is once you understand the theory well,
I kept calling you. I presented my notebook to
the code, all the code looks simple and easy to understand.
Come here.
Harini, we need to put you on mute. Okay, so this is it, guys. So that's all I have for today. I suppose it's already 9 o'clock, so you guys can have your break. I would suggest that I'll close today from now. If anybody has questions, you ask. We are done with today's session, but do the labs, guys. Do play with it and create new examples. Go to 3 dimensions, do this, do that. Create more clusters. Play with the data and see how it works. And play with all these other algorithms. The whole point of PyOD is you can, with one line of code, change from one algorithm to another, and there are 30 of them here close to. 20, 30 of them. Go play with all of them. Any questions?
As if I do, but it's not related to today's topic. We needed your time tomorrow, so can
Sure.
you?
I'll give you for your project, right? I'll give
Yeah.
you. Definitely, I'll give you time.
What time, or you'll let us know later?
It's very hard to tell. My days are not my own.
Okay.
I have to, like for this, I have about a half an hour. I have 1 hour to have dinner, then get into India meetings. Life is busy. All right, guys. So have fun. No one is asking questions. I will stop the recording. And guys, please do take the quiz, right? Because otherwise we are in a peculiar situation. All the data suggests that you guys have fallen way behind. Your projects are behind. Your quizzes are behind. But at the same time, at least a subset of you want us to go faster. So you see the divergence between intentions, good intentions, and reality. So catch up if you can. That's it, guys.
Bye. Are we coming back right now, or
you're
standing?
There is no coming back.
Can we'll just submit questions on the lab channel in Slack?
Yeah, you can do that. I mean, if you guys want me, I can linger around for another half an hour while you do the lab.
Like, I mean, for me, I have actually run through the entire lab while you were walking through it. So now it's more playing with it. So if you're going to come back, you can do that too.
Right. So, all right, go have your dinner. I'll have my dinner and I'll be watching out the channel. And if needed, I can keep the Slack going. I mean, this meeting going.
Thank you, Asif.
Okay.
Asif, sir?
Mm-hmm.
The last quiz, can you make it multi-attempts, please?
Not yet, actually. It screws up the statistics. See, what happens is that sometimes I get the impression that more than half the class has taken. And then when I go in there, it turns out that 4 people have taken it 3 times.
Okay, because I lost some connection and I had to leave it halfway. I couldn't complete it. No worries, I'll do it after the review. No worries.
Yeah, I can do that. Sorry about that. I'll see if I can just reset it for you so that you can do it. Yeah, I'm just trying to keep track of how many people have done it. Eventually, I'll make it all multi-choice so you can keep repeating it later on.
Thank you, sir.
You're welcome. Are you guys liking the quiz, or why is it the attendance is so poor in that? Is it not proving useful, the quizzes?
No, it's very useful.
I think people
are definitely useful
on themselves. I think they need to just jump in and go ahead and take the quiz, and even if they do terribly, you'll learn from it.
That's right. That's right. The point is that this is not there's no your annual reviews are not based on the reports from these quizzes, right? Your annual performance reviews. So you learn. It's a reality check. That's all. Suppose you get -4. What does it mean? Your understanding is on shaky foundations at this moment. You need to go back and review and come back and take the quiz at a later time again. And in a few attempts, when you notice that your scores are becoming closer to max, you know that you have picked up the subject, the topic. All right, guys.
Thank you, Asif.
Thank you, Asif.
Thank you.
Thank you.
Thank you, Asif.
Sure. Yeah.
Thank you.
Thank you, Asif.
Asif, I think I can't. I tried the quiz. I don't think I can retake the last one, the word embeddings.
The word, yeah. At this moment, as I said, right, I've disabled the retakes because otherwise I don't get the statistics of how many people have taken it. What happens is that some people take it 3-4 times, and it looks as though the whole class has taken it.
Oh,
Because
I
if
got
you have the situation right now where half the people who have taken it want to take it again.
Yeah, I don't want to. Let everyone take it. And after a couple of weeks, when I know that no more attempts are likely to come, I'll open it up again to repeat. And also, you shouldn't take a quiz right immediately afterwards because you have seen the answer. You should wait for a couple of weeks so that you have forgotten the answers from the quiz. And then you have studied the subject, and then you'll have a more realistic score. Otherwise, if you have taken the quiz, I give you the answers, you'll remember that, and you'll retake the quiz in your mind. Some of them will still be remembered, and then you will get a skewed understanding of your score. Of your a skewed sense of your understanding of the topic. So I have to wait to get the answers.
That's a question.
Yeah.
For the PhD thing that you were trying to do, what would be sort of the daily structure?